Hello and welcome to the Postcard Professor, where we take complex ideas and explain them in the space of a postcard.
In this series of videos, we're going to be exploring the concept of the conservation of momentum. To start talking about that, we really need to discuss what momentum is, and on top of that, how impulses are applied to change momentum. So this video is focused on the ideas of impulse and momentum. I think the place to start with this is the force equation that we used in kinetics. So we have typically the sum of the forces is equal to mass times acceleration. But we can think of acceleration as simply the change in velocity over time. And what this does for us is it allows us to rearrange this equation as the sum of the forces being equal to the change in this quantity m times v with respect to time. So we actually made this a little bit more general than what we had before, right? Because now we're saying that our mass is allowed to change in time, whereas up here we make the assumption that it's constant. This quantity that appears here, we're going to label as the momentum. And a lot of places, if you're searching online or wherever else, you'll see this listed as a value p. Now this is in general a vector quantity because our velocity here is a vector quantity. I'm going to stick with just the mv notation. It's easy enough to write out, so I'm going to leave that as it is. But if you see p elsewhere, all this means is m times v. All right, so let's see what's going on here. We're saying that we have some object, and I'm going to limit this to one dimension for now. And this object has some mass, and it has some velocity. So we would say that this has a momentum of m times v1. I'm going to say that this is the state at time t1, and we're interested in what happens between time t1 and time t2. So I'm going to make the assumption that our mass is not changing, but we're going to have some variation in the velocity, and of course our time is changing. Now, the piece of the picture we haven't looked at yet is what's happening with these forces. Well, between these two states, we're saying that there's going to be some force applied. So I'm going to say that there's some force F that is pushing this object to the right. And the result of this force is an increase in the momentum. Now, let's take a step back and perform some calculus on this basic equation. So we have two times, and we'd like to integrate between these two times. So let's take the integral from time 1 to time 2 of both sides of this equation. On the left-hand side, we just have our force. And on the right-hand side, we're integrating a derivative. So this right-hand side just becomes the two endpoints. So we can say that this is mass times velocity 2 minus mass times velocity 1. And we know that from the fundamental theorem of calculus. Let's write that in a slightly more useful form. So let's have the mass times the velocity, 1, on the left-hand side, along with this integral of the force. And on the right-hand side, all we have is the mass times the velocity at state 2. This integral right here is the other half of what we're talking about today. This is the impulse. So essentially, this impulse is just the sum of all the forces over the time between our two states. So to illustrate this, let's look at an example. We're again going to have these objects, and I'm going to simplify it again just to one dimension. So let's say that this object has a mass of 10 kilograms, and that's not going to change. And then we're going to look at two separate times again. So our time 1, I'm just going to give this a value of 0 seconds. And I'm going to say that time 2 is just 2 seconds later. We're going to have some force applied. And this force is going to cause a change in the velocity. So we need an initial velocity as well. And I'm just going to set the velocity at state 1 equal to 0 meters per second. And I'm going to say that we don't know what the velocity at state 2 is. But we do know that if the force is to the right, that this is going to be moving to the right. So now we need some information about our force. I'm going to generalize this a bit and say that our force is actually time varying. We're taking the integral over time, so this is no problem. So the force increases linearly up to a point. And I'm going to say that this occurs at 1 second. And then after that, it stays constant. It can continue on, but we're interested in everything up to 2 seconds. This vertical axis is our force. We're going to measure that in newtons. And our horizontal axis is time, and we're measuring that in seconds. And let's give this a value as well. Let's say that this is 100 newtons. So now we can look at this equation up here and do a little bit of math. So mass times velocity 1 plus this integral from t1 is 0 seconds to t2, which is 2 seconds, of this force, which is changing with respect to time. That is equal to mass times this unknown velocity v2. So easy things first. We can get rid of this because v1 is equal to 0. Then all we need to do is integrate this term, and we'll be able to solve for v2. Easy way of doing integrals is just to find the area under the curve. Let's look at this first piece first. We have a triangle with a base of 1 second and a height of 100 newtons. So this becomes 100 newton seconds divided by 2. So just 50 newton seconds. This second piece is going to be the area of the rectangle, which is just 100 times 1. So we end up with 100 newton seconds. Just a quick note on units. A newton second is simply a kilogram meter per second squared multiplied by seconds. And so one of the seconds cancels out with this, and we end up with kilograms meters per second. So we have our mass unit and we have our velocity unit. Our integral of the force here becomes 150 kilograms meters per second, which is equal to 10 kilograms multiplied by our unknown velocity. And so this math is pretty simple. We end up with the answer that V2 is equal to 15 meters per second. So now that we have that, we're done. That's all we need to do for our little example. And hopefully this illustrates how these forces that we apply relate to our momentums. As a side note, everything that we've done here today, you could still get to relatively easily just using our kinematic equations. This is useful because it introduces these two concepts, which we're going to be using in the next several videos to think of things that are quite a bit more complex.